Hello everyone. So here are part 2 of your notes for 10.2, finding arc measures. So first thing we're going to go ahead and talk about is the arc addition postulate. Now, we've gone over a different postulate from first semester. That was the segment addition postulate. The arc addition postulate is almost the same. It's just we are adding arcs instead of adding segments. So in the picture here, we have arc ABC, and if we wanted to find the measure of arc ABC, keep in mind that when we name these arcs, if I am referring to a much larger arc or a major arc, I do need to use a third point, so that's why I'm calling this one ABC. And if it is made up of smaller arcs, then what the arc addition postulate tells us is that we can add these arcs together. So the measure of arc ABC will be equal to the measure of arc AB added together with the measure of arc BC. And that's all there is to it. Sometimes we might need to subtract because sometimes we might be given the larger arc. And then what we're asked to find is one of the smaller pieces instead. But regardless, if you use this equation and substitute in, you will be able to solve for the missing part, whatever the problem is asking for. All right, so let's go ahead and let's actually take a look at an example. So in example 1, they tell us to find the measure of arc LM. So arc LM is here. And currently it is 6x plus 45 degrees. And they also tell us that segment PM is a diameter in circle K. Now, something that I want to mention about the diameter, it's really important that we know why they're giving it to us. So if segment PM, this one here is a diameter, what this diameter provides for us is a semicircle. And that semicircle goes from P to L and all the way over to M. Now, the reason why semicircles are important is because we know that semicircles, or the measures of semicircles, are equal to 180 degrees. So, what this means is that the measure of arc PLM, this is equal to 180 degrees. Now, before I go ahead and write that down though, taking a look, I notice that arc PLM, the semicircle, is made up of two other arcs, specifically arc PL and arc LM. So I can use the segment addition postulate to write an equation that tells me that if I add the measure of arc PL together with the measure of arc LM, it will give me the measure of arc PLM. And now we can go ahead and substitute. Again, arc PLM is a semicircle, so it's 180 degrees. And this will be equal to the measure of arc PL, which is 3x, plus the measure of arc LM, which is 6x plus 45. Let's go ahead and solve for x using algebra. I'm going to go ahead and combine my like terms. So we get 180 degrees is equal to 3x plus 6x gives me 9x plus 45. I'm going to go ahead and subtract 45 on both sides, since what we're trying to do is we're trying to solve for x right now. 180 minus 45 degrees is 135 degrees. And this is all equal to 9x. Final step, we need to divide on both sides by 9. My 9's on the right side cancel out, and I'm left with x is equal to 15. Now, at this moment, I'm technically not done. Yes, we finished solving for x, but the problem is asking us to find the measure of arc LM. And x does not represent the measure of arc LM. So what we'll have to do is we will have to substitute into the equation to find the measure of arc LM. So the measure of arc LM is 6x plus 45. So if I were to go ahead and substitute this in, I get 6 times 15 plus 45. And if you put this all into a calculator, we find that the measure of arc LM is equal to 135 degrees. And that is the entire problem solved all the way through. All right, so go ahead and pause the video here and see if you can give this one a try on your own. All right, go ahead and check over your answers. Now, for this particular problem, because they want us to find the measure of GF here, first of all, I don't have any semicircles to work with, so 180 degrees is kind of out the door at the moment. However, what I do see is that the measure of arc GEF, if I were to add this arc together with arc GF, this will give me 360 degrees. So what we did here was we found the measure of arc GHF by adding all of these arcs together with the arc addition postulate. And then once more with the arc addition postulate, I knew that if I added these two arcs together, I would get 360 degrees. I substituted in for the measure of arc GHF and finished solving for the measure of arc GF. All right, now let's go ahead and let's talk about this theorem. It's called the congruent central angles theorem. Now, before we can actually talk about the theorem itself, there's a requirement that needs to be fulfilled before we are actually able to use this theorem. So here's what we need. We have two options. Option number one is that we are working inside one circle, and I'll explain what that means in a moment. So that's option number one. Or option number two is that we are working with congruent circles. All right, now, congruent circles means that you have two circles that are exactly the same size. Circles already have the same shape, so we don't need to worry about that. But how do you know if circles have the same size? Well, their radius measure would be the same. Because if one radius is larger than the other, then one circle is going to be bigger than the other. So if they have the same radius lengths, that means that the circles themselves are the same size. Okay. Now, here's a tricky one that you might want to keep in mind. We can have two circles that have the same center, and they look kind of like a little target that you might throw darts at or shoot arrows at, or maybe it looks like when you throw a rock into a pond or a pool, and these are the ripples that come out from where the rock landed in the water. These are called concentric circles. And here's the thing with concentric circles. Because I have one circle on the inside of the other, the circle on the inside has to be smaller than the circle on the outside. So this leads me to the fact that concentric circles are not congruent. So if you see concentric circles, we do not have congruent circles. So keep that in mind. All right, but let's suppose that you are working inside one circle. So this picture over here, we only have one circle to worry about. We don't have two different circles where you have to check to make sure that their radius are congruent. So we fall into option number one. We are working inside one circle. So because of this, if we have congruent angles. So if angle BAO, if that angle is congruent to angle RAN, then what I'm allowed to assume is that their related arcs are also congruent. In other words, arc BO will be congruent to arc RN. Now, the reverse is actually also true as well. You don't have to have congruent angles in order to have congruent arcs. We can actually go backwards. You can have congruent arcs and then make the conclusion that you have congruent angles. So this arrow actually goes in two different directions. But keep in mind that in order for us to have congruent angles or even congruent arcs, you either need to be working inside one circle, which is what we have here, or you need to have congruent circles. So this is the case where you have two or more circles, but double check to make sure that their radius is congruent. All right, so let's take a moment and let's actually go over an example to help explain this. So in example 2 here, it tells, or rather it's asking us if the red arcs are congruent, and they want us to explain why or why not. Okay, so the two arcs that we are trying to consider are arc RS and arc TU. So arc RS is here and arc TU is here. Now, this is a picture, or rather these circles are concentric circles. They have the same center. One is inside of the other. Now, keep in mind what I said earlier. Concentric circles are not congruent. So because I do not have congruent circles, this tells me that my two arcs, arc RS and arc TU, are not congruent. And the reason for this is because the circles are not congruent. Okay. So, again, we fall under, this is technically the second option. We're working with more than one circle. There are two circles here. So we have to double check to make sure that they are congruent. But the radius for the circle on the inside is much shorter than the radius for the circle on the outside. So the radius are different lengths, which means that the circles are not congruent. And by that, we can now say that the two arcs are also not congruent. All right, go ahead and pause the video here and see if you can give this one a try on your own. All right, so go ahead and double check over your reasoning. Now, again, the first thing I need to look at is to determine whether or not my two circles are congruent. And yes, in fact, they are, because the radius is marked on both circles as having the same length. So that satisfies the first condition. That tells me that both of my circle, T and X, are congruent. The second thing to check, if I did have congruent circles, was to make sure that I had the same angle measures. Because here's the thing, if the angle measures are different, then the arcs are not congruent. But because both angles here measure 95 degrees, my two red arcs are in fact congruent. So that's what I mentioned in the explanation. I said that both circles are congruent and I have congruent angles as well. So long as you said something about the angles being equal or the angles being 95 degrees, and you mentioned something about the circles being congruent, that explanation is good enough. All right, so that's it for this video. Thank you very much for watching.